Good afternoon, and welcome to the Music and Technology Seminar at Carnegie Mellon. Our guest today is Evan O'Doherty, whose official bio lists many international prizes in advanced mathematics. His unofficial bio shows a distinguished background in music in both piano studies and composition. Evan garnered international attention this past March when he was featured on a CMU webpage playing his piano piece illustrating the first 97 digits of pi, which of course Evan knew from memory. The digits of pi are mapped to notes of the D major scale, with 0 mapped to the C sharp at the bottom end and 9 mapped to E natural at the top. Although the whole piece can stand brilliantly on its own, you can see a fascinating animation by BXA student Davis Baldwin of the digits unfolding as Evan plays the piece. Please welcome Evan O'Doherty to the Music and Technology Seminar at Carnegie Mellon.
So, I'm going to talk about music and math, and I'm going to start with a question that I get asked all too often, which is music mathematical? Can you all hear me okay?
Yeah, we can hear you great.
Yes.
And the reason I say I get asked this too often is that when people ask this question, they're usually thinking of things like this. And while it's certainly true that there's a lot of math in the sense of counting beats in music and counting sharps and flats in the circle of fifths and the study of tuning systems, how the octave and the perfect fifth generate everything. Somehow this doesn't get to the heart of what music is. And so when people observe that mathematicians are often pretty good at music, yes, mathematicians are competent with this kind of stuff, but there must be something more. And I want to get at that something more today. And in particular, now we've got a bunch of music generated by AI. I can't confirm this, but I saw a headline today that an AI-generated pop song has topped the charts. But as you know, AI is terribly bad unless you tell it to do otherwise at drawing calendars. It doesn't know how to count or even how many days there should be in a week. And the same thing for music. So I found this video perhaps a year ago, and maybe the AIs have improved since then, but AI versus Mozart, can you tell the difference? And so Ray Chan is putting himself to the task, to the test. And so there's a pair of tracks, one being from some real piece from the epic, but not from one of the most famous pieces of them, and then one by AI. And so the question is, can you tell which is which? And can you tell without looking at my face?
Before and have mixed up the order. So we've got different categories. We're going to start with Baroque music first. That sounds really good. This is definitely Baroque music. Okay, we gotta listen to the second one before making any comments.
Any guesses?
Wow.
The second one is the AI, and there are some giveaways, but in particular that ending, that cadences are very particular. There's something incoherent about that. That flat nine in there doesn't quite belong, and there's something about the anticipation of the tonic that comes too soon. There should be a hunger for the tonic. this would be a more authentic way of doing it. So there's something in the music that the robots haven't caught on to, and perhaps it's partly a function of how we teach music that the folks at the AI companies can't figure out what's missing either. But anyway, I want to try to somehow get at that. So let's take a detour. Sudoku got popular in the early 2000s, and it replaced things like detective puzzles that there had been in the newspapers. Before then, it's very simple. You just have 1 through 9. You're trying to make every row, column, and box have all the numbers from 1 to 9. And part of the appeal of Sudoku is that you can have puzzles of different difficulty levels. This one says expert in some language, and so it can be very challenging to figure out how to fill in the numbers. But when you've got the puzzle filled in, to check the solution is easy. You just go through each row, column, and box, and you say either it's correct or there was a mistake. And so there is this distinction between finding the solution and checking the solution. That is an example of what computer scientists call the distinction between P and NP. So I'm going to get a little bit technical, trying not to get too lost in the weeds. So we say that a task, whatever it might be, is of class P for polynomial if it can be finished quickly. So it's something that can be done. You think of what the task is and you can do it. So for example, if you have two n-digit numbers, so n could be a number like 100, you have a 100-digit number and another 100-digit number, and you want to multiply them together, well, you've got to multiply each digit of one by each digit of the other, so that's 10,000 multiplications, and then you've got to add all those together. So it's tedious, but it's something a computer can do in a fraction of a second. Now, suppose that you're doing something else. So a task is of class NP. NP stands for non-deterministic polynomial, so it basically means that you can do it in a polynomial time, but with certain choices having been made that you couldn't necessarily predict beforehand. So it means that the completion can be verified quickly, but we may not have a good algorithm for completing the task itself. And a good example of something that has this characteristic is factoring. So 3 times 7 is 21, but if you have 21, to try to find the factors 3 and 7 that give that is harder because, for instance, if you want to factor a 200-digit integer into its two 100-digit prime factors, meaning that they can't be factored further, then you might have to try something like 10 to the 100th different factors, where that's a lot bigger than 10,000. And there are better factoring algorithms, and computers have gotten fairly fast, but it's still not nearly as fast as multiplication. So finding the solution is hard, verifying the solution is easy. And one of the 7 Millennium Prize problems is P equals NP? So in other words, can every task of class NP, like factoring, actually be done in P time, in polynomial time? So if you show that P does not equal NP, that no such algorithm exists, then you'll make $1 million. And if you show that P equals NP, then you'll probably make a lot more than $1 million because you'll be able to crack the crypto systems that make a lot of our communications secure. So this problem remains open. But most people are kind of convinced, although there's no formal mathematical proof, that P does not equal NP. In other words, that tasks of this class, like factoring, are intrinsically much harder. And to me, that seems like an attractive hypothesis, because it means that certain things really are hard that can nevertheless be apprehended not so difficultly. So, for example, here are some NP problems that are believed not to be in class P. Factoring an integer into primes. Another one is Boolean satisfiability. So a statement like A and not A is a contradiction in terms. It cannot be true. But suppose you've got a sentence like A or not B, and B or not C, and C or not A. As you add more and more connectives and more variables that can either be true or false, it becomes harder and harder to guess whether there's a combination of values which makes the whole statement true. And again, satisfiability, SAT solvers have gotten faster, but it remains NP hard. It's not been cracked in time P. Another one's the knapsack problem. You have this bag that can hold 15 kilograms, and the question is there some subset of these books that exactly equal 15 kilograms? In this instance, there are. You can add 12 plus 1 plus 2, and that's 15. And so once you see the solution, verifying it is quick. But if you imagine there's hundreds of books and the size of the knapsack is 1,000,000 kilograms, it can get hard. And dare I say it, Sudoku is also NP hard. And in fact, some Japanese engineers proved in 2003 that Sudoku is actually NP complete, that any of these other problems can actually be translated in polynomial time into a Sudoku puzzle whose solution encodes the solution to the original problem. So what does this have to do with music? The main thesis that I'd like to present today is that creating a great piece of music should be at least NP hard. It should be at least as hard as any of these problems. And what evidence do I have for that? Well, all of you before you were musicians were listeners of music. And presumably you had the experience of listening to a piece of music and saying, wow, I couldn't have come up with that, but now that I hear it, I know that's good. And so maybe you got the sheet music and you learned to play it on an instrument, note by note, and as you hear those notes, again, you have the sense that I never could have come up with this combination of notes. But now that I hear it, that's the right note. It's that piece that I love. And so I'm not claiming that music is reducible to mathematics, that it's entirely a computer science problem that can be phrased algorithmically. If so, it wouldn't be music. It would be some logic puzzle just like Sudoku. But what I am claiming is that there should be some aspect of this NP versus P dichotomy, some goals that are easy to state and easy to check if they're verified, but hard to fulfill. This quest for the difficult good should be a part of music making. So we live in a time when there used to be rules for making music, and now it seems like all rules have been long since thrown out the window. So what standards do we have? It's tempting to think that everything is just a matter of taste. And you know what the old saying about taste is. There's no disputing about taste. And in particular, we shouldn't let the tastes of dead white men determine what we like. These ideas are very much in vogue. But I'm trying to present that there's something more to it than taste. So we then have a responsibility to form our own musical tastes based on what we listen to. It should be consistent with human nature. So sugar is sweet. We look at candy and we see something attractive to eat. A major triad is also sweet, especially if it's approached in such a way that it's difficult to achieve, say from dissonance. There's something about that arrival. So some composers have had trouble with that. For instance, Scriabin tried to form a musical language where the tritone was the basic interval. And he made some interesting sounds, and he even had a mathematical justification for choosing the tritone. It divides the octave in two equal parts. But you hear that, and the overtones of those notes are dissonant with each other. There's a dissonance there. It's objectively less consonant than the perfect fifth, for example, which divides the frequency ratio not in geometric progression, but in arithmetic progression. That's a stable interval. So we should be mindful of these things, how they sound. At the same time, we should be open to new sounds. We don't have to be old fuds listening to the same music over and over again. And lastly, we shouldn't be easily satisfied by trivial solutions. What do I mean by trivial solutions? I mean things like this. There are a lot of pop songs that use 4 chords, and often it's the same 4 chords. If you look up the 1, 5, 6, 4 progression on Wikipedia, there's hundreds of songs that use the same chords. And then what melodies do they play over those chords? There's a sense of indifference that there might be consonance or dissonance. You can play any notes of the scale over any chords. This kind of indifference is kind of concerning to me. Hatred is less dangerous than indifference. The composers of the jazz age had a certain hatred for convention, for the pure triad, and so forth, and so they would make bigger chords which have their own beauty and internal logic to them. But indifference doesn't drive you forward. It doesn't challenge you to make sounds that have more and higher coherence to them. So, where do we get these NP-hard elements in the music making? The first one I'd like to point out is counterpoint. What is counterpoint? It's also known as polyphony. I'm going to use those two terms synonymously in this talk. It's the art of combining more than one melody at the same time. Here is a piece of counterpoint from the 12th century in France, Benedicamus Domino, and it starts in the middle of the manuscript, so if you can't see, there is one voice that starts right here where my cursor is, and it goes very florid, and then the second voice, the bass line, starts right here, and it goes slow moving bass line. It's a while before you get to so fast, a florid melody, slow-moving bass line. Is that the kind of convention still with us now? Yes. You hear there's a party above you, and what do you hear? The bass line. Slow-moving bass line, the melody is more florid. That's the convention in just about everywhere in the world, whether it's Indian music, Indonesian. The exception would be Jamaican music, where they have the tradition of the steel drum, which is an accompaniment instrument, but it sounds in the high register, and then the melody is more florid below that. So reggae, for example, comes out of that kind of tradition. But so this is counterpoint, and it's existed in Western music for a very long time, and so we easily forget that not all nations have had counterpoint all the time. And so if you look at music like this is an Ottoman military march. And so on. You hear there's a lot of cymbals, a lot of percussion, enough to strike fear in all your enemies. And there's also some instruments, but they're all playing the melody. There's no harmony and there's no counterpoint. And so, little by little, the outgrowth of things like this French polyphony have spread around the world. Now just about everyone has heard American pop music, and so there's many musical styles out there. But when we stop to think about what does counterpoint entail and what are the desiderata that inform it. And so I'm going to say goals/rules. If you took a class in musical composition, harmony or counterpoint, you probably saw these. And these goals and rules have been rigorous to different degrees in different times in music history. But they are still operative today in some forms. So one is melodic continuity. So you want to have melodies that are singable so you don't leap by too large an interval or a tritone or any of these unless you have some particular reason to do so. A second one is harmonic consonance. So there are certain chords that we like. So you can form counterpoint where the voices only make consonances, or if you have a dissonance, there should be some certain preparation. And one of the most beautiful kinds of dissonances is the suspension. We've been using it since the Renaissance. And it's when you have a note that is carried through from the previous chord and then resolves, usually downwards. So instead of going da, 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 you can go da, 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 da. A third desideratum is tonal coherence. We don't want to just hear random notes. We want to think that some scale, such as the diatonic scale, is in control. And if we hear a chromatic note, a note that's outside of the scale, we want to hear it as something, as a leading tone, as something leading somewhere. So sharp 4 is a leading tone to 5. Yet another one is thematic unity. So there isn't just one piece, there are many pieces, and they have different themes. And forms like the fugue and the sonata help to give a conventionalized and understandable way for these themes to disappear and then return. And yet another is voice independence. So this is related to that notion of avoiding trivial solutions that I noticed before, because you can fulfill items 1 through 4 just by having voices that parallel each other either in octaves or in fifths. And when people were first inventing counterpoint, this sounded really good, and in a way it does, but then they started thinking, oh, we can be more subtle if instead of just we can have more contrary motion. So a melody going up and a bass going down. Now, more than 2 voices can't move in more than 2 directions, and so there's a whole art of counterpoint, and there were compromises made to make the rules in such a way that they're flexible for all kinds of themes, and yet strict enough to allow one to show skill by writing a piece that obeys all these rules simultaneously. And pieces that show skill in an especially concentrated degree is a canon. So maybe you've sung a round like Frère Jacques, dormez-vous. And a lot of rounds work by just by having a tune that is just based on one chord. And so as 2 or more singers sing that at different times, you build up the chord, and so they harmonize with one another. Row, row, row your boat is another one based on one chord. That's not the case with this piece. This is by Palestrina, who's often considered the greatest composer of the Renaissance, and he wrote a lot of pieces. I think this one deserves to be better known because it is a canon. So this is modern notation. If you read it in the original, there would be a notation of just this melody. And so it's a melody that goes Pleni sun celi et terra. It has a certain melodic shape to it, certain rhythms characteristic of the time period. And if you take a modal counterpoint class, you learn about the style of Palestrina, and you learn the skills that it would take to make a 2-voice canon, where you have 2 parts, like the bottom 2 parts of this one, singing in displacement. So you see the basses start, and then the tenors come in 1 beat later and a 4th higher, so from G to C. So Pleni sun celi et terra. So that's a canon. And Palestrina could have stopped there, but he didn't. He added a 3rd voice. And the remarkable thing about this canon is that both the time and pitch displacements are changed. So from bass to tenor, it's a distance of 1 beat and a 4th. From tenor to treble, it's a displacement of a 5th and 2 beats. And this is not easy. Very few composers, even in the Renaissance, attempted an asymmetric canon like this. But he manages to get the consonances just right. Pleni sunt celi et terra, pleni sunt, and so forth. And it goes on for a while. So to recapitulate, what makes this particularly hard, and definitely an NP hard problem in my experience, is that you've got three directions. Just as a Sudoku has rows, columns, and boxes, and it's easy to fulfill one of those, it's moderately hard to fulfill two, but it can be diabolically difficult to fulfill all three. Likewise, a canon, your melodic continuity is going across each staff. Your harmonies are the vertical sonorities that you get. And he's able to get good harmonies. But then the thematic unity, which is a desideratum of a lot of styles, he does it completely strictly, having all three voices sing the exact same melody. And this is quite an achievement. And so what do we mathematicians do when we find something remarkable? We write a paper about it. And so this is a paper that I published in the Journal of Mathematics and Music. And what I did is I analyzed the schemes of different canons in the Renaissance repertoire specifically. Although you could go forward, but I haven't seen modern or even Baroque or classical composers venture in this direction. So in particular, I wanted to see which schemes are possible. So a fourth up, a beat later, a fifth up, 2 beats later. That is the scheme of this canon. If he tried to do a fourth up, a beat later, and then a fifth up, another beat later, it would not work. The trouble is that all of these consonances between the lower two would be imitated mostly with dissonances between the upper two, and so it would be very inflexible. You can satisfy the rules of the style for a while, just with a sequence that repeats the same motive over and over again. He did not want to do that, so we found a scheme that works. And I found that, indeed, Palestrina found schemes that work, but he didn't find all the schemes that work. And so I wrote a new canon in Renaissance style, and I chose a theme from one of Palestrina's most best-known works, Sicut cervus desiderat ad fontes. Sicut cervus is one of the most frequently performed Renaissance sacred motets today, and Sicut cervus is not a canon, but it is imitative polyphony. So he sacrifices exact imitation of the theme by putting minor variations on the theme in each voice so that he can get the rest. He can get richer chords, he can get clearer cadences, and so forth. And so I decided to see, can you rework Sicut cervus to be a canon? And so I used the words Benedictus qui venit in nomine Domini. These are the ones that are sung right after the consecration and the elevation of the host in the traditional Catholic Mass. And so Renaissance composers would often use pieces like canons to put music to that sense of awe that is specific to that time in the Mass. By the way, I sing in a choir about a 20-minute drive from Pittsburgh in at the Institute of Christ the King Parish, and so I've become intimately aware of these liturgical issues too. So this is how I wrote the canon. Benedictus, Benedictus, qui venit, Benedictus, and so forth. So it goes on for a while, and it uses a couple themes from Sicut cervus. So that is the first source of NP. Oh, and by the way, I want to mention that the scheme of this is 4 beats later up a fifth, 3 beats later up a fourth. And so this was one of the schemes that Palestrina never used, but I proved that it is actually workable. There's another source of NP structure. Many of you presumably have memorized this speech. The Gettysburg Address begins 77 years ago. And what did Lincoln do? Well, he lived in a pivotal point in our nation's history, in the war against slavery, but he also put to work some principles that he learned from reading Dickens and countless other authors that he could read in the time that he lived, and that is the art of crafting a longer sentence. So you make sentences out of meaningful parts. So 77 years ago, that is complete as a clause, but it's not complete as a sentence. It functions as an adverb. It has the same role in the sentence as a word like yesterday. And so we're used to language having meaning, and we're used to putting together meaningful units to express the meaning that we want. And it's often said that music is a language. In order to keep music as a language, or as many languages, because there are many musics in the world, we need to keep the meaning alive. And what is the analog of long-range meaning in music? I would argue it's exemplified by something like this. This is Beethoven's First Symphony in a piano arrangement. And Beethoven did something radical. What did he do? He started it like this. Authentic cadence in F major, but the symphony is not in F major. Deceptive cadence onto A minor, but the symphony is not in A minor. Another cadence on the key of G. So he's getting at the main key, which if you didn't know is C major, by going all around it. So he could have written it like this, with the F major and the A minor, and then gone directly to the C. But he stretched it out. So after he finally hits the tonic, but it's an inversion. It's not this. It's got the third on the bass. And then he keeps going. He finally hits the tonic, but now the third is on the treble. You got root in the bass. So he's constantly skirting the tonic, but you feel the pull of the tonic. He could have gone forever. In fact, there are some piano concertos where he adds more. The tension isn't resolved until we get to where it says allegro in the middle of the score. So what did that theme consist of? It consisted of a big 1 chord, a big 2 chord, a big 5 chord. So what he could have done in 2 seconds, he stretches out into a few bars, and certain composers like Wagner could do this for hours at a time, stretch on the tension. And I say that this is long-range meaning because each of the little motives has a certain function in the short term and in the long term. And if you're really clever, you can get those two to have contrasting meanings. So for example, this first chord, in the short term, it's a dominant. But in the long term, it's actually C, it's the tonic. And so retrospectively, after we have heard the whole introduction, we realize that he did not start on a random chord. He started on the tonic, but with a tendency tone inserted, so that we would have to wait to hear that it actually is the tonic. It's 1 dominant 7th, which is a consonant, say, in a blues style, but it's a dissonance in this classical style, but it's not the most dissonant chord that one can use. So it hesitates between a a dominant and a tonic, and it confidently shows both of those roles. Yet another source of NP structure in music has to do with how we do voice leading. And so I'm going to draw here from Dmitry Timochko, who is a professor at Princeton in the music department, and I'm going to draw from his book, A Geometry of Music. There is a lot of nonsense written about math and music, including, dare I say, in the Journal of Math and Music, where I published my results. Timochko is not the sort who writes nonsense. His book has a lot of insights in it, and I'm going to just draw on one theorem. So it's a mathematical result. He proved it, although I'm not going to describe it in mathematical detail today. And he did it by analyzing the extended common practice, as he describes it. He wants to say that going all the way from medieval music past the usual era of classical music all the way into jazz, there is a consistency of practice that we can draw, and in particular in the way that tonality is lived out and the way that voice leading is lived out. There are two often at odds with each other desiderata. One is voice leading parsimony. You want your melodies, your polyphonic parts to be roughly stepwise. And secondly, you want harmonic consistency. You want to have certain recurring chords. And these are at odds with each other. And you can get both of them in two cases. Chords that are nearly even or very uneven in the way that they divide the octave. So a triad, a major triad, divides the octave roughly evenly. It's 4 half steps from C to E, it's 3 half steps from E to G, and it's 5 steps from G to C. So 4, 3, and 5 are roughly equal. The only more equal threefold division in the octave would be the augmented triad. And the augmented triad is less interesting than the major triad, both because it's more dissonant, it's not acoustically consonant, and also because it's non-invertible. It only has one form. So if you use triads, then because the triad is nearly even, you can get stepwise voice leading between different transpositions and inversions of that chord. The second case in which you can get something like that is if the chord is very uneven. And that would sound something like this. So you have a 3-note tone cluster that divides the octave very unevenly into 1 half step, 1 half step, and 10 half steps. So if you have a chord built of those, you can kind of make music by swapping the notes of those chords. It's so dissonant, though, that you could use this perhaps for certain scenes in a film. Ligeti, who's most known for writing the score of 2001: A Space Odyssey, would experiment with sounds like this, but by itself it's kind of too dissonant for the concert hall. But that means that chords that are neither nearly even nor very uneven pose a special challenge because the voice leading parsimony will not be immediately there. So as it is for other nearly even chords like the dominant 7th chord, you can move to other dominant 7th chords with short movements. And so this is a challenge, and as a mathematician and as a composer, I'm interested in a challenge. And I'm not the first one to take up this particular challenge. So this is an excerpt from Morten Lauridsen. There might be some Lauridsen fans in the audience. And what did he do? He has a certain harmonic palette. He has a couple of favorite chords, one of which is the triad with an added 9th. So why do we like the sound? It's part of the overtone series. So if you start from a low fundamental tone and you build up the overtones, The first chord you get is the open fifth, also known as the power chord. It was a staple in medieval music, and it's still a staple in heavy metal. And then the next is the triad. And then the next one, the seventh harmonic, is approximately the dominant seventh chord. But and that's what you would get as a basic consonance in the blues, but it lies a little bit out of our scale system, and so if we're looking for new sounds, we can try the next harmonic, which is the ninth. It's a kind of nice coincidence that the ninth harmonic is the ninth of the scale. Very warm sound. And if you invert that, you get the triad with added fourth. Or maybe this. Another chord that's not quite so settled, but it works well in the same environment. So Lauridsen takes these chords and he manages to find some pretty good voice leadings, even though, according to Timachko's theorem, he's not able to do the minimum, which you can with triads and seventh chords. And so he goes like this. So starting on a really crunchy spacing, and then working his way toward consonants. Look at that switch. He goes from the add 4 to the add 9 by just moving one note. He moves. You can move one note also like this. He does that in quite a few of his pieces also, moving the third and taking advantage of the fact that we can tolerate skipwise bass lines a little more than skipwise movement in the melody or other voices. And so, qui tollis peccata mundi. There's a rich chord, and so he's gotten through by using these add 9 and add 4 chords in different positions. A few incomplete ones. A few passing tones. This is an unstable chord, a 4/2 chord. So that's also a 7th chord. And finally we arrive back at the desired chord. So to wrap things up, we contrast classical and modern music, and whatever those terms mean, and we see in modern music certain trends, like the first was an emancipation of the rule against parallels. So Debussy would use parallel triads, or even parallel dissonant chords. And you can do that. And more generally, free harmony, emancipation of dissonance, polychords, polytonality, combining different layers. And atonality, the lack of tonal organization, the lack of metric organization. Spoken words, things like rap and compositions in mixed media. And more recently, all these electronic timbres, noise generators, use of distortion, and so on and so on. And what I want to say, I don't want to say all these things are bad, but I do want to say that all of them are in themselves of class P. If you want to do it, you just do it. You use these techniques, and if you do this, if you're lucky, you'll end up somewhere at the beginning of a program, or more likely in the middle of a concert program. But to advance, to be a greater composer, I would argue that you have to be mindful of these NP level elements that have been present in classical music and music since the Middle Ages, and which some of the truly great composers today are very much mindful of as well. Among them, I would movie composers, people like John Williams, James Horner, Andrew Lloyd Webber. These musicals, this music is very well appreciated everywhere. And let's not forget Joe Hisaishi, who came to Pittsburgh a couple months ago. And the program had its middle and its end of Joe Hisaishi's music, and not just everywhere. Not just anyone can write at that level. So to conclude, I've got a little piece of music, if you don't mind me running a slight bit over time. It's a piece that I wrote. It includes some of these techniques that I've been demonstrating here. In particular, it does use some Lauridsen-style harmony. It is known as ritornello. So what is a ritornello? It's a Baroque style originally found in opera, where you had the theme returning in different keys, and this is a piece that does that. It's also in a funny looking time signature that I called 5-star. What does 5-star mean? It means that you have 5 pulsations, but they can be any length. So I was inspired by, say, readings of Shakespeare sonnets, where it's all in iambic pentameter, so everything is a 1, a 2, a 3, a 4, a 5. But good poetic readers don't read every line with that same rhythm. It might go a 1, a 2, a 3, a 4, a 5, a 1, a 2, a 3, a 4, a 5, a 1, a 2, a 3, a 4, a 5. So I wanted to see if I could make that in music, and it seemed like there was something waiting to be written. So without further ado, here's my piece, Ritornello. Already I'm using the added ninth. What did I just do there? I added a fourth, but not in the way that preserves the root. I reinterpreted this D flat add 4 as a G flat major 7 9. And then I do a sequence in the melody, but I keep the bass note the same. Not all melodies can do that. By the way, if you want to hear this piece without me jabbering, you can go onto YouTube or Spotify. We've got about 8 songs up. Major seconds and added dissonance, you can still hear the tritone as remaining unstable. So that's the key. It's not that there's no dissonance, but that you can tell the difference between some dissonances and some consonances. Thank you for listening.
Evan, that was really terrific.
Thank you. I'm glad you could all tune in.
Any comments or questions from anyone in here or online?
I have a question.
Go ahead.
So you said that, so like on that slide where you had like like the parallel fifths and all those things, like with the new age of music, right, and stuff like that, right?
You're
Post,
talking about where I talk about the
post,
modern things.
yeah, post romantic techniques or something, right?
Yes.
Does that mean that like a piece of that was composed by Ravel is a P problem, not an NP problem?
So yeah, so each of these composers, people like Ravel, there was an NP problem. It's just that it may not be obvious what they solved. It may not even be written down anywhere. But there's a reason why they're remembered, and many other composers who lived at the same time have been forgotten.
I would I would argue that like Debussy and Ravel, for example, right?
Yeah.
Having the choice to break the rules, and they studied counterpoint rigorously, right?
They did, yeah. And if you go into Debussy, you find that there's a dichotomy. When Debussy wants to write a chord stream, he does it. But when he wants to write counterpoint, he does that too. And what he doesn't do, which unfortunately many modern music students do, is mix them indiscriminately, where you can have a counterpoint with a blemish of a pair of parallel octaves or fifths that seems to me like they just didn't notice it or didn't want to be bothered to pay attention to that sound and how it's different than the texture around it.
But wouldn't like the problem of like for Ravel example, right? Like
Hmm.
placing counterpoint in a way that would sound like grammatically correct, I guess, in your terms, right? Wouldn't that also be part of the problem? Wouldn't that be another parameter? Right?
Yeah, so in these composers, you can also hear long range meaning, and so it's not easy what they did to create that. That's right.
Okay. Thank you.
We got a
I know that your presentation wasn't primarily about AI, but it was interesting how you sort of introduced the presentation um, as many things like artificial intelligence sort of complicating this problem and this discussion.
Mhm.
I was just wondering if, like, in all of the fields that you're in, what do you think about AI as being a disruptor to both like math or also music?
Yeah, there's a lot of people looking at AI. And so, for context, there were headlines last year that an AI system solved, for example, problems in the Math Olympiad. And when we look at how the AI did it, we see that ChatGPT by itself produces a lot of nonsense. But you pair it with a system like Lean. If you look at the back of my laptop, there's a sticker that says Lean. What is Lean? It's a system for computer aided proof checking. So it's a computer language, and you type your theorem statement into Lean, and then you type a set of tactics like apply this theorem or prove it by contradiction, and Lean reads your program and applies those tactics. And if at the end of applying those tactics, the hypotheses match the conclusion, then Lean says done. And so it's a way of deterministically verifying that a proof is complete. And so there's now 5 gigabytes of math that's been stored in Lean in the MathLib library. And so, what these AI firms were doing is they would train their bot on Lean code and get it to generate Lean code. And then they would, and then to solve an IMO problem, somebody would translate the problem into Lean. And then the chatbot would try to solve it. And you would feed the output into Lean, and Lean says, sorry, syntax error on line 6. And the chatbot takes that and revises its solution, and you keep going back and forth. You can do thousands of iterations of this, and at the end, if Lean says that is correct, then you know that you have a verified proof. So what I'd like to point out is that this depends very much on human input. So the AI is trained on Lean proofs that people wrote. It also rests on the presence of ideas in mathematics being formalized in Lean. Right now, we're not yet at the stage where every field of mathematics is formalized in Lean. People are still pouring a lot of money and time into that. For instance, Kevin Buzzard is trying to code up a proof of Fermat's last theorem in Lean and got a huge grant from the British analog of the National Science Foundation for that. And so what I see is that the AI can help as it progresses. It can help remove some of the grunt work. I can see us getting to a point where we just type a proof or a proof technique, and the robot says, "Yeah, that works." But it's not going to replace the work of mathematicians to come up with new ideas. And likewise, I can't imagine it replacing the work of musicians and music aficionados as deciding what goals are worthy and what pieces are worth writing and listening to.
I have a question. So based on the criteria of what makes a good music and
Yeah.
your definition, so if AI is able to satisfy those criteria at some point, does it mean that P equals NP in this specific scenario of music?
um, so, yeah, I can see that certain styles, like probably the style of Palestrina, has the most written about it of any style in music. It's incredibly disciplined. There are so many rhythms that he could have written and didn't, and it would be an something that computer programmers have been trying to do for 40 years, and it would be a great achievement if they finally did, to code a computer program that can generate music in that style. And I mean, there are different ways of putting our knowledge out. We usually write papers or we compose songs, and writing an AI program is yet another form of human achievement.
So the P versus NP, I think makes a lot of sense for the long-term composition, but
Yeah.
because it's kind of an asymptotical approach. But what about things that are pretty short? Like, I don't know, let's say you want to make a 30-second or even like jingle or just like a, hey, can you compose over this? Do you think that's like a feasible program to write and execute and
It's a good question. So, right, so in order for P equals NP to be mathematically meaningful, you have to have problems that come in different sizes, and you have to be able to let the size go to infinity. In practice, we can't do that. We can't listen to 100-hour pieces of music. But in practice, the distinction becomes manifest not very far. So maybe a 4x4 Sudoku is pretty trivial. A 9x9 Sudoku already has all of the tricks that you would need for the bigger ones. Like, have you ever seen a monster Sudoku, a 16x16? It's very time consuming, but you mostly use the same tricks. And it's definitely harder to solve than just to verify the solution. And so likewise in music, you try to write a two-measure piece, and there's not so many competing demands that go into it. If you're writing a jingle for some product, so there is most of the concerns are going to be extra musical. It's going to be, does this match what the product is in some way that we might not be able to quantify? But once we get to even say like a 32-bar jazz standard, composing something like that, there's enough possibilities that it takes skill.
So, Evan, I'm curious to know, did your pi piece follow the N or the NP principle?
So yeah, 97 digits of pi. I wrote it in some of the same style that I've just been demonstrating. I put quite a few Lauridsen style chords in there, and I definitely feel like I had to think in order to write that piece. And in particular, on top of the usual demands of music composition, I put one that's entirely unusual. I think the only you can find precedents for it. I'm not the only one to write the pi song. Josquin Desprez wrote pieces like the Missa Hercules Dux Ferrare, where he takes a phrase and translates the letters in it, in this case the vowels, into musical notes, and he gives a theme. And then he creates counterpoint on that theme. So it's one of these these desiderata that I think ramps up the NP quality of it because, in particular, the if I can find it, yep. Oops. Here is the piece, and the digits of pi because they're random. So to everyone believes, although we don't have a proof of it, that pi is a normal number. That means that the digits will pass any statistical test of randomness, where you test to see if in each base the digits are equally distributed. And so in some parts of the piece, I had to negotiate leaps in the melody and find a good harmony for that. And then I found other motives. So I found other motives, other themes, so that I set myself a challenge to satisfy the usual requirements of a piece of music while at the same time using the digits of pi in the foreground all the way through.
Evan, I remember asking you why only 97? Why not round it off to 100?
Yeah, so when you look through random data, you're always going to find patterns of some sort. That's how the human mind is. We can find patterns in anything. And in this case, the digits of pi, even though they go on forever, they have certain cadences. And in particular, the end of this piece, I found a cadence point in pi. The next four digits would be 7067, and that would throw it completely off.
I have a question.
Yeah.
Did you look at the next 97 and see if they made any sense at all?
I've looked. Yeah, I haven't found a cadence that's quite as usable for that. So obviously you could keep going farther and farther out, and eventually there will be another cadence. But by then the piece would be just kind of ungainly long, and having no cadences before that, it's not so great. But I think Teddy has a question.
Oh, yeah. Thank you for your talk. It was very interesting. So for the NP problems that you were talking about, are these, from what I'm understanding, is that most of these problems aren't, have they been turned into like an NP problem, like concretely, or is it more like,
So you're talking about the slide where I talk about examples of various problems.
yeah.
This one? This one?
Hold on, let me check. Switch.
Or are you talking in
I'm talking
reference
about like
to
the music examples, right?
Yeah.
Like the counterpoint and the voice leading. Like, are those problems like, I guess how would you even turn a problem like that into like an
Yeah,
NP
so
problem, right?
I tried to mathematize canons, and what I did was I simplified. I stripped everything down to its essentials. I said, what if you just use whole notes and you have only one rule, which is basically harmonic consonants. So you're not allowed to have two voices a step apart at the same time. And so based on that one rule, I analyzed canons. And in this case, there is some kind of NP flavor as far as if you've got a canon to try and figure out if it will continue further. But in practice, with that kind of simplicity, the computer could exhaustively try the combinations. Now, if you go beyond that to something closer to the style of Palestrina, where you've got different rhythms and you've also got rules about parallel octaves and about the treatment of suspensions and many different things, as well as the melodic contour. That's a big part of the Palestrina style. Then I can imagine formalizing enough of this to the point where a computer would go through and try a few canons and reject them, or find that after a while they do not continue and back up, just as you do if you're trying to solve a maze with a computer. You back up and you try a different continuation. And so if I see behavior like that, then that's evidence that I've gone perhaps a little beyond P into NP.
Thank you. That's very interesting. And then also, does that mean, okay, so like going to the P equals NP question, if we find out somehow that like P equals NP with
Yeah.
and all these like I guess ideas in music, I don't know, like what do you think that would mean for like I guess all these perhaps NP type um musical like frameworks, right? Do you think
Yeah,
like
so some say
computers start
that,
taking over like that?
yeah, personally, I don't think P does equal NP. But even if it did, the exponent, the M, in solving these NP complete problems would no doubt be so huge that it would be almost as hard as an exponential problem anyway.
Okay, I see. So you don't think it's like as helpful as you think it would like it be in practice, is what you're saying.
Yeah. And music takes place at the finite level. We're not looking to solve. We're not looking to somehow make bigger and bigger pieces of music in some sense.
Any other questions?
Yeah, I have a question. If we go back to the digits of pi problem,
Yeah.
did you compare digits of E?
Oh
And
yeah. E is
also,
believed to be a normal number. Also, you could do it with any random sequence of digits.
did you compare which produce a more musical one, like digits of pi or digits of E? Did you compare the two? Like, what is more musical to our ears?
I've seen. So there was somebody in a science fair who put out a poster that claimed that the golden ratio phi is the most musical
Exactly.
of all numbers. And I looked at the evidence, and there was just a lack of mathematical understanding. So all of these numbers should be normal. So in the long run, all of them should be equally musical or equally unmusical, in the sense that they just have essentially random digits, and the same in any base. So maybe you write these in base 5, and then you've only got 5 notes, so there's no tritone, and so in a way it's easier to do the music with just 1, 2, 3, 4, and 5, and you can create a piece like that. And then the challenge might be to add variety in the accompanying parts to craft a musical form. So I think you can do the same thing with any irrational number. I chose pi because there's a long tradition of memorizing digits of pi, and in particular, CMU had a pi
Mhm.
recitation contest one year, and there were people who knew over 100 digits of pi.
Yeah, it's maybe like good experiment for you. Like you probably pick like E, pi, and golden ratio, then
Yeah.
give to a bunch of kids or like someone they don't know anything about this. You don't tell which one is, and just ask them like, what is your best one, and see whether there's a pattern. Maybe why some people like maybe like there's a trend without telling anything about which one is which. We just like give like a five of them and ask them to write, evaluate them, pick the best one, and see whether they like whether many people go 10 to one of them. And if it
Yeah.
is, maybe you have a theory, like, oh, there
Hmm.
is something going on. So maybe something like I'm
Yeah.
just thank you, thank you.
I have one quick question too. Thank you, Evan, for the talk. This was fascinating.
Hi, Max. Thank you.
I have a question. So you had mentioned at the end a lot of these forms of modern music in classify in P rather than NP. Do you think that this is kind of that we have something left to discover, something left in NP that we haven't some form of complexity in music that's pleasing to the ear that we haven't come across yet that's going to be developed through modern music? Or do you think kind of all of these main forms have kind of already been described, already been discovered?
I think it's endless. So, the medievals kind of spent 500 years seeing what you can do with fifths. And then from the Renaissance till the 20th century, we kind of spent 500 years figuring out what you can do with triads and using things like the dominant seventh as your dissonances. And now I'm doing Lauridsen and many other composers are seeing what you can do if you have the add 9 chord as your basic consonants. So this is for the first time using a non-consecutive group of harmonics because I'm skipping the 7th harmonic. And just as using the triad as Dufay did paved the way for imitative counterpoint fugue and such, I think that if people approach the add 9 chord with that same kind of openness to see what it leads to, there can easily be new forms lying in wait.
So, Evan, is there any prediction of what will be the case in 50, 100, or 500 years?
I'm not going to try to guess. For example, when you use triads, the 5-1 cadence has emerged as paramount. And it took a while for that to catch on. So in the medieval times, the usual cadence was usually something we could describe as a 2-1 or a 7-1, stepwise motion. And when you think naturally, that is how it should be, because the bass line is a voice just like the other ones, and it can resolve with stepwise motion. So when people were using triads at first, so one of the earliest pieces that's come down to us that uses the triad as the basic consonants is called Summer is a Comin in, which is Middle English for summer or spring really has arrived, it's one of the first examples of what we know in pop as the ostinato bass. But the chord progression is 1-2. Summer is a comin in through the cuckoo. So the bass line goes 1-2-1, and so this was the norm until about 1450, when people like Dunstable and Dufay started using the 5-1 cadence. Although Machaut used a lot of cadences, and occasionally he would use 5-1 also. When people have looked at Lauridsen, they found that there's a lot of plagal motion, so a lot of use of the 4-1 cadence. And when you listen to pop music, there's a lot of 1-5-6-4-1. So maybe we're going to see a resurgence in the use of the plagal cadence, not as an adjunct to the authentic cadence, which it often is in classical music, but as a primary cadence in its own right. But then I've also done pieces that use Lauridsen style of harmony and use 5-1 cadences. So there's a lot of room for exploration.
So at least we have a lot of things to look back on and bring up again.
Mm-hmm. And Max, you sent me a question over email also about what you do with secondary dominants, because in my pedal matrix harmony webpage, I mentioned adding the tonic and dominant to different chords. So, and then the question was, what happens if you have a secondary dominant? You can get some jazz chords out of that don't quite fit into the style. Or what I kind of like to do is to add not the 5 and 1 of the main key, but of the temporary key. And that has the interesting side effect that you notice the tonicization is starting to happen before you even hear any chromatic notes. So you can have your tonic as your added note. And then if we switch, you see what I just did there? I used E, which is the median of the main key, as the added pedal tone, and so I've just tonicized A minor without using any chromatic notes, and I can use chromatic notes if I want to. I can return to the original key by adding that C to it. So yeah, I think many styles remain to be discovered.
Evan, thank you so much for being here today. We really appreciate it.
It's my pleasure.
And I'll just close by saying to be continued.